Yeah, welcome everyone to this week's Physics Meets ML. Happy New Year to everyone. We're very happy to have Nadav Cohen here today, joining us from Tel Aviv University, where he's currently a professor. He has a background in electrical engineering and mathematics, and spent some time at the IIS and Princeton. And now, we are very excited to hear his view on, how we can capture the behavior of neural networks, and in particular also how this can be or is close to physical systems, in particular things that can be described with tensor network techniques. So we are very much looking forward to your talk, Nadav, and please take it away. The floor is yours.
Thank you very much. Very happy to be here. Thanks for the invitation. So first of all, if there are any technical issues, anything like that, please let me know as soon as possible, and I will try to fix the setup. Other than that, I divided the talk today to two parts. One is an overview of the area of deep learning theory. I was assuming that not every person in the crowd works in this area or knows it very well. So the first part's kind of high level, describes the area and the different questions. And then it's a deep dive into a series of works that utilize quantum tensor networks to try and answer or address part of the pressing questions in deep learning theory. So if I'm a little bit off and the first part is trivial, please let me know and we can move quickly, go through it and reach kind of the core of the talk. Okay. All right, so deep learning probably needs no introduction. I guess we all would not be here without this technology. It's really transforming a lot of application domains. Nonetheless, it has a secret, or maybe it's not such a secret, that we don't really understand what's going on there. We don't know why these algorithms work the way they do, what makes one model better than the other. And many people, including myself, believe that it's important to understand this technology, not just for scientific curiosity, but also because technologies that we understand tend to work better than ones that we don't. And this is especially important for critical application domains, like, I don't know, self-driving cars or medical applications, where the last thing you want is an algorithm that you don't understand causing a disaster by making a decision that you don't understand. So I hope I've convinced that understanding what's going on there is important. And as said, I'll start with kind of an overview of the area of deep learning theory, what it means, in my view, to have a mathematical understanding of the technology. And again, this is going to be kind of soft and high level, possibly trivial to some, but I hope for others it might be interesting. Okay, so if you want to formally talk about deep learning, you have to start with statistical machine learning, because deep learning ultimately is a special case. And let's lay out the basic statistical learning setup. So we have an instance space. That's a set of objects that we would like to infer something about. For example, if we're interested in saying something about 100 by 100 binary images, we could represent them as 100 by 100 matrices, each entry holding 0 or 1. We have a label space. Okay? This is the set of possible labels that we can assign to instances. It could be continuous if we're measuring some continuous property, or it could be discrete if we're classifying. There is some distribution over labeled instances. Okay? The world is probabilistic. We don't know this distribution, but we do assume that it exists. And we have a loss function. Okay? This is a function that intakes two labels and returns a non-negative number that indicates the extent to which the labels deviate from one another. And so if the labels are continuous, I could use squared difference, and I could also use other types of losses. And the basic framework, the basic task in supervised learning, in statistical learning, in the supervised case, is that I'm giving a training set S which are M labeled instances, pairs xi, yi. I assume that they are drawn IID independently from the world's distribution. And given this training set, my job is to return a predictor, which is a function from instances to labels. And I want to return the predictor that minimizes the population loss. What's the population loss? That is the average loss, the average discrepancy between the true label and the prediction, where the average is over the world's distribution. And so I want to minimize this thing by proper choice of H, of a predictor. This is obviously highly non-trivial because I don't even know D. Okay, so even if I had infinite computational power, I can't compute this thing. The basic approach, if you sweep away a lot of the details in statistical learning, is as follows. I predetermine a class of predictors. Okay? That's a class of functions from instances to labels. And given the training set, I return the predictor in that class, in that family, that minimizes the empirical loss. What's the empirical loss? It is, again, the average loss, the average discrepancy between the true label and the prediction. But now the average is taken over the training set. So this is something that I can compute. Okay, you give me an H, I run through the training set and just measure the average loss. And I will return the predictor that minimizes this thing. That's the approach. Okay? Now, here's a picture of what's going on. Okay? In gray here, this is an illustration of all the possible functions from instances to labels. Okay? Somewhere within that big set of functions lies the optimal function. We denote this by f star d. It does not depend on the training set in any way. It doesn't depend on us. It's a property of the world. In H, this is the class of predictors that we fixed in advance. Right? Within it lies some optimal predictor, H star D. This depends on the choice of predictor class, but it does not depend on the training set. This is the predictor that is optimal on the training set, meaning it minimizes the empirical loss. So theoretically, we should be able to find this thing. All we need to do is go through all the predictors in this class, measure the empirical loss of each of them, and return the minimizer. In practice, this search is often something that can't be done efficiently, can't be solved exactly and efficiently, so we return some approximation H bar. We care about the population loss of H bar, and it is determined by three factors. The first one is called approximation error, also referred to as expressiveness. And this results from the fact that our choice of predictor class does not necessarily include the perfect function. Yeah, so there's some penalty that we pay here. The second results from the fact that the training set is finite. It's called estimation error, also known as generalization. And if the training set were infinite, then a predictor doing a good job on the training set would probably also do a good severe is known as training error, or and this again results from the fact that we can't always find this thing exactly. Sometimes we only return an approximation. And in its basic form, statistical learning theory is all about these three factors, these three sources of error, and how they trade off with one another. And they behave in ways in deep learning that are very different from what we're used to in classical machine learning. Okay, so let's say a few words about that. So classical machine learning, it's not exactly a well-defined term, but let's think of linear predictors. Okay, so they could have different loss functions, would lead to different models like support vector machine or least squares regression. And in this case, the problems are set up in a way that the empirical loss minimization is a convex program. That search for H star S boils down to a convex program. For those that don't know, it pretty much means that I'm minimizing some kind of objective that looks like a big bowl. And so if it looks like a big bowl, I can do it exactly efficiently in reasonable time. And therefore, I'm basically able to find this H star S. So H bar is basically equal to H star S, meaning there is no training error. this source of error is 0. And in terms of the others, the estimation error and the approximation error, we have a famous phenomenon known as bias variance trade-off, which roughly speaking states that if I expand my predictor class, I make it bigger, obviously the approximation error will go down because I only include more predictors. However, the estimation error will go up. I will be more prone to overfitting. And vice versa. If I shrink the predictor class, I pay in terms of approximation error, but I will likely overfit less. So the estimation error will go down. And this is the trade-off that governs the generalization. And all in all, I think it's safe to say that the theoretical learning community has a feeling that we have a decent understanding of what goes on here. In deep learning, the situation is very, very different. Okay, the predictor classes are no longer linear. They consist of compositions of transformations, one on top of the other. Each of these transformations is parametric and it's called a layer. You can have different types of transformations. We'll give you different neural network architectures. And there are various different models, but what's common to all of them is this compositionality, composing nonlinear transformations, one on top of the other. With neural networks, with these models in deep learning, the empirical loss minimization, the search for H star S, is no longer a convex program. It's now non-convex. And we know that H star S is not unique. There are many different predictors that have low empirical loss. Many different predictors are optimal in terms of the training set. And for some reason that we don't really understand, gradient descent, which is a super simple algorithm that just takes steps in the steepest direction iteratively, somehow it's able to reach one of these H star S's. In terms of estimation error and approximation error, generalization and expressiveness, the situation is even more peculiar. That is that we know for a fact that some of the predictors that reach low empirical error, some of them also have low population error, low population loss, so they generalize well, but others don't. And for some reason, with natural data, with the kind of data on which deep learning works, the predictors that are found by gradient descent are often ones that do generalize well. So somehow it's able to find the good solutions in standard natural settings. And maybe most surprisingly is the fact that if you take your predictor class and you make it larger, you increase the size of your model, then the approximation error goes down, that's obvious. But in practice, the estimation error oftentimes also goes down. So larger models generalize better. And this seems to almost contradict the bias variance trade-off. And the theory of deep learning in its basic form is around answering these different questions. And it's still deeply under construction, I would say. A few years back, I would say that we don't understand anything. Today, I think we understand much more, but there's still a lot that we don't understand. And this is basically the area that I am interested in exploring. And I will talk today about applications of concepts from quantum physics to better understand these topics. So if there are questions at this point, this is a good time. And otherwise, we could just move on. All right, let's head on. So now we'll talk about implicit regularization in quantum tensor networks. This is based on a series of papers from the last several years, NeurIPS and ICML. The first one was done in Princeton with Sanjeev Arora and students Wu and Yuping Luo. Wei is now an assistant professor in Michigan, I believe. And the latter three works are with my students, Noam Razin and Asaf Malan. Okay, so let's start by talking about implicit regularization. What does that mean? So as we said, classically, generalization is understood through the bias variance trade-off, which means that you want a model that is rich enough to fit your data, but you don't want it to be too rich, right? Because then you will overfit, you'll fit the noise. On the other hand, if your model is too simple, you're not going to be able to fit the data. And there's some sweet spot in between. Okay, so you want really the right capacity, not too much, not too little. And the way that the capacity is controlled usually is either by limiting the size of your model, okay, the predictor class limiting its size, or by adding regularization, okay, for example, L2 penalty. However, in deep learning with neural networks, we often see that they do generalize even when they have no explicit regularization, and despite having many, many more parameters than training data. Even in these regimes, they generalize. The conventional wisdom around this is that there is some kind of implicit regularization. There's no explicit regularization, but there is an implicit regularization. And that implicit regularization somehow steers gradient descent towards solutions that are simple. Okay? Hence, they generalize. So that's the intuition. And a goal of deep learning theory is to mathematically ground this intuition, okay? Mathematically characterize the implicit regularization at play. What we're going to do today is talk about quantum tensor networks and their implicit regularization. But beforehand, let's think about linear regression. Okay? This is a very simple model. We kind of turn to that as probably the simplest case where you can consider the notion of implicit regularization. And it's known for linear regression that when the number of learned weights is larger than the number of training examples, when the model is over-parameterized and you don't have any explicit regularization, gradient descent initialized at 0 converges to the minimum L2 norm solution. And this is a classic known result. Initialize gradient descent at 0, you train with a linear model that is over-parameterized, you will hit the solution with lowest Euclidean norm. There is a hope that in deep learning, gradient descent also finds a solution minimum norm. So maybe it's not Euclidean norm, maybe it's some other norm, but gradient descent is somehow steered towards solutions that have minimal norm in some appropriate sense. And this was demonstrated in various different settings, simplified ones. And what we're going to do is explore this prospect and look at implicit regularization in quantum tensor networks, okay, or tensor networks. That's usually how they're called. Why do we want to study them? So maybe here it requires a bit less explanation, but in general, so first of all, they are equivalent to certain types of neural networks, okay, nonlinear ones with polynomial nonlinearities. This is something that has been shown several years back. They have been, because of this fact of their equivalence to neural nets, they've been used heavily for analyzing passiveness in deep learning. This is something that colleagues and myself did a few years back, and others as well. They're not used in practice as commonly as other models, but they do deliver promising performance. I do believe that if the community spent more time, the empirical community spent more time working with these models, they would be made to work even better than they do, and they already deliver competitive performance. And finally, maybe they're more suitable for kind of quantum devices. Maybe they will fit more naturally in quantum machine learning in the future. So that's why they're interesting to look at. And what we're going to do is now analyze the implicit regularization in tensor networks. Okay, so what are tensor networks? I assume many of you know, but just for the sake of it, we'll go through this quickly. These are graphs where vertices correspond to tensors, which for our sake are just multidimensional arrays, and edges correspond to modes, to axes. A mode is refers to an axis. Okay, so node, a vertex, without any edges is a scalar. If there's one edge, that means there's one axis, it's a vector. If there are two edges, it's a matrix. Three edges, it's kind of a cube, and so forth. And when I have an edge connecting two vertices, that represents contraction. So if I take two vertices, connect, and I have an edge connecting them, then on the left, that's a vector. On the right, that's a vector. And by connecting them, I take their inner product. Over here on the left, it's a matrix. On the right, it's a matrix. And by connecting them, this is matrix multiplication. I end up with a matrix. There are two open edges here. Okay, so how do tensor networks or tensors relate to machine learning? So apparently, you can think of the process of tensor completion as a prediction problem. And what do I mean by that? Tensor completion is a problem where we are given a subset of entries from some unknown tensor. Okay, so denote them by y, I1 to in. I1 to in range over some observed indices. And there are many, many entries in the tensor that I do not see. And what I want to do is infer them. So you can think of this, you can think of a D1 by D2 by Dn tensor completion problem as a prediction problem where the input's a tuple. The tuple has n elements. An element j ranges between 1 and dj. So these are my inputs and my outputs are the reals. Under this viewpoint, the value of entry I1 to in the tensor, that corresponds to the label of the input I1 to in. The observed entries, that is the training data. The unobserved entries, that's the test data. And a tensor is just a predictor. Okay? It assigns a label to every possible input. So how does that connect quantum tensor networks to neural networks? It connects it through the following observation. Doing tensor completion with a quantum tensor network, that precisely corresponds to solving a prediction problem for a neural network. Okay? Under this correspondence, the entry in the tensor represented by the tensor network, the quantum tensor network, that is exactly the output of the neural network when I feed in the input I1 to in. Okay, so entry I1 to in the tensor represented by the tensor network, that's the output of the neural network when I send an input I1 to in. The structure, the topology of the tensor network, that will determine the architecture of the neural network. And different types of tensor networks, like what you see here on the left, will give you different types of neural networks. Okay? And then you can study these neural networks by looking at the tensor networks and taking advantage of concepts and tools that have been developed in the context of tensor networks. Okay? All right. So,
sorry, can I ask a quick question?
Yeah.
You list a couple of architectures here, right? So how complete is that list, or how far can it be pushed, or has it been pushed in terms of which neural network architectures can you capture?
That's a great question. So first of all, I'm going to go through each one of these three in more detail. The first one is it's a very, very simple neural network. The other ones are similar to convolutional, or basically some type of convolutional networks. This has also been used for recurrent networks, like MPS style tensor networks correspond to RNNs. It has also been used for self-attention models, like transformers, something that my former group at the Hebrew University did. They also did the RNNs. We have a recent work, very recent one, doing graph neural networks. So it can be taken farther than what I'm showing today. I'm just showing kind of a bread and butter basic architectures, but it can be taken farther. For example, with the three models I mentioned, RNN, self-attention, and graph neural nets.
Yeah. Thanks.
Okay. All right, so now let's go through these three models from simple to more elaborate. We'll start with the simplest, which is a kind of a chain topology. So a chain quantum tensor network. Let's consider the case of ordered 2 tensor completion, meaning matrix completion. Chain quantum tensor network, we're going to abbreviate it as CQTN, C for chain. That corresponds to a linear neural network, which is basically a fully connected neural network with no activations. Okay, so the inputs multiplied by a matrix W1, then multiplied by W2, and so forth until WL. Using this for matrix completion corresponds to parameterizing the solution as a product of matrices and then fitting the observations through gradient descent. Okay, so the loss looks like this. I sum over the observed entries, and I take the square difference between the observed value and what model holds at that location. So the observed value at location ij, what my model holds at location ij, and I parameterize the model as a product of L matrices. And I have this parameterization, just optimize it with gradient descent. Okay. So this is known as matrix factorization. And an important note is that we choose the matrices to be such that the hidden dimensions here are large enough to not constrain the rank. Okay, I don't want to limit the search space in any way. I do not want to impose any explicit regularization. Any regularization that we may have here is going to be implicit because I choose the hidden dimensions here to be large so I can represent anything. Okay. So this is the model, and it has been conjectured by Gunnasecker et al. A few years back that gradient descent over this model, if it is initialized near 0 and it's run with a small step size, then it will find the solution with minimal nuclei. And this is a conjecture that's been made. And what we are going to do is carry out a dynamical analysis of what goes on here, and then use it to try and address the validity of this conjecture. All right, so let's look at the dynamics. So we denote by WE the product of all the matrices. We call this the end matrix. And we let sigma CR, these are the singular values of this matrix. C stands for chain, R is the index of the singular value. And what we prove is that when I run gradient descent on this model, on the chain model, with small initialization and small step size, then the singular values evolve at a rate that is proportional to their size to the power of something. And that something is 2 minus 2 over L. L, number of nodes, the number of vertices in the chain. It's the depth. Okay? So the larger L is, the larger this power is. And what this means, what these dynamics mean, is that if a singular value is very small, then its movement is slow. And if it's large, its movement is large. So if I initialize close to 0, the singular values move very, very, very slowly. And then as the loss kind of decreases, those singular values that reach a critical threshold will start moving quickly. And so you can imagine this kind of incremental learning effect. And that's exactly what happens in practice. And this is a standard experiment. This x-axis is the number of iterations, y-axis, these are the singular values. And you can see their behavior through time in a low-rate matrix completion problem with a chain model. And you can see that they start off near 0, and then one after the other, they pass this critical threshold, start moving quickly. And you end up with a small number of singular values that are large, and all the rest are very close to 0. So this incremental learning leads to a low rank solution. And this was further formalized by Lee et al. On work from a year and something ago. And an interesting consequence of this dynamical result is as follows. It can easily be used to show that there exist matrix completion settings where the implicit regularization of this model, this chain model, drives all the different norms. No matter what norm you have, it's going to be driven towards infinity, while the rank is basically minimized. So you can show that there exist such settings. Hence, it is not the case that the implicit regularization always minimizes a norm, because there exist cases where that norm would go to infinity, whereas the rank is actually being minimized. So the implicit regularization of this chain model is not a minimization of a norm. And this also happens empirically. You can see it in that very simple setting. You can see that when the loss goes to 0, the norm basically goes to infinity. And so that's the simplest model. And now let's move on to something a little bit more elaborate. So the tensor network that we're going to look at now has a star structure. Now we're thinking of general completion. And this is the model. We call the star tensor network, so SQTN. It has this star structure, and here there's a delta tensor, which means a tensor with 1 on the super diagonal and 0 elsewhere. That corresponds to a nonlinear model. It's a shallow nonlinear convolutional net. The nonlinearity here is polynomial. It's products it's multiplicative. And this is the neural network that the star tensor network corresponds to. And solving tensor completion with this model means that you parameterize the solution as a sum of products. Okay, so just like before, my loss is the sum over the observed indices, and I take the square difference between the observed value and what my model holds at the same location. And now my model is parameterized as a sum of outer products. Okay, sum from R equals 1 to capital R of these vectors, the outer product between. That's what it boils down to. And this is something that's known as a CP factorization. The CP rank of a tensor in general is the minimal number of components. We call each outer product of this form a component. So it's the minimal number of components, the minimal number of capital R here that you need. In order to express a given tensor, that will be its CP rank. And we consider the case where this R, capital R, is large enough to not constrain the CP rank. So you could actually represent any tensor. There is no explicit regularization here. If there is any regularization, it is going to be implicit. Okay. All right. So what we do here is just like before, we analyze the dynamics. We now denote by sigma SR. That is the Frobenius norm, okay, of the rth component. S here stands for star. We show, just like before, that gradient descent on this model, if it has small step size and it's initialized near 0, then these component norms evolve at a rate that is proportional to their size to the power of 2 minus 2 over n. Okay, and here that's the order of the tensor. You can see that just like before, just like in the chain case, the component norms here move slowly when they are small, and they move quickly when they are large, and you get the exact same incremental learning effect, just like you had with the chain case and matrix completion. With a star case and tensor completion, you have this incremental learning effect. These are now component norms. You end up with a small number of component norms that are large. All the rest are very close to 0. That means low CP rank. Okay, so the incremental learning here leads to low CP rank. What we can show formally, and derive this.
Can I ask a question just to keep understanding on the neural network side? What does this correspond to when I have this kind of transition to large component norms? Is there something I can understand? What's happening there?
What does it mean for the neural network? So the way to think about this is as follows. The neural network learns a predictor, right? And for any, you give me an assignment of weights, that is a predictor. That's a function. That function, I can think of it as a tensor. And the CP rank corresponds to that function. So the neural network learns a function with low CP rank. This is a property of the function. It's not a property of the, it's not something that is limited to the model. It's a property of the function.
Okay.
So you say, which is at the end of the day, I would argue this is what we are interested in, right? At the end of the day, machine learning, deep learning, this is all a means to learn a function. Yeah. And the question is, what kind of functions do these models learn? So this is the characteristic of the functions.
So is it somewhat that I'm learning a different mode or something like that? Is this?
What is it? Oh, you're asking. So what does it mean that my function has low rank?
Yeah. Yeah, effectively.
It does have a very concrete meaning, rank for a function. I'll actually get to that.
Okay.
Yeah. Okay. So what we can show and derive this end-to-end result, we can show that if a tensor completion has a CP rank 1 solution, in that special case, we can formally prove that the star tensor network is going to reach it. Okay, so in that case, it's not just a dynamical analysis. We can actually prove what kind of solution that it will reach a low rank solution. All right, let's now move to the last model, which is a tree. Okay. So here we have a tree quantum tensor network. It looks like the star, but you have these local, small local star models, right? You have these little delta tensors. And that corresponds to a deep nonlinear convolutional net. The fact that we moved from a star, which is a shallow tree, to a general tree, which is deep, that in the neural network viewpoint means that we moved from a shallow neural network to a deep neural network. In this tree, we have local sums components, or sums of local components. Okay, so there's a local sum component here. And in general, if I have a tensor that can be represented by a tree with a small number of local components in each location, that means informally that the tensor has low hierarchical rank. Okay, so low hierarchical rank is a property of a tensor. And if I can represent the tensor as a tree with a small number of local components, that means there is a low hierarchical rank. Again, we analyze the dynamics. Now, sigma TR, T stands for tree, R is an index. That's the Frobenius norm of the rth local component in some location of the tree. The delta tensor in that location, I denote its order, the number of edges there by capital M. And what we show here is that gradient descent on this model with a small initialization and small step size leads the local component norms to evolve at a rate that is proportional to their size, to them, to the power of 2 minus 2 over m. Okay, so again, I have this power, and this means, just like before, that when these local component norms are small, they move slowly. When they are large, they move quickly. And I get dynamics that are similar to those that I had in the chain and star cases. Okay? And this happens empirically just as well. You start off near zero, the local component norms barely move, and then they start shooting up one after the other. I get this incremental learning phenomenon. I end up with a small number of local components that are large. All the rest are close to zero. That means I have low hierarchical rank. Okay? So in the chain case, we had low matrix rank. In the star case, we had low CP rank. In the tree case, we have low hierarchical rank. Each one of these is a generalization of the former. It's kind of, these models generalize one another. All right, let's now talk about what this actually means. Okay, so we took these models, we characterized the dynamics of gradient descent on them. We have this incremental low rank learning phenomenon, and we showed that it can't be characterized as minimization of a norm. But what does that actually mean in practice, okay, for deep learning? So there's several implications. I'll mention here 3. One is a very practical one. Something you can do is just take a neural network, a standard one, take one of its layers or more, some of its layers, and just parameterize them as tensor networks. Just parameterize them that way. In this case, you will get this low rank structure, which means that your layers are compressible. Right? They're compressible, and that can improve generalization. This is actually something that's being done. See, there are practitioners that actually do this today. And this is a work from Facebook AI, Jan LeCun's group that did this. There's another group from NVIDIA, MIT, various other works that I'm not mentioning here. And you could just try this. Okay, no theory, nothing, just take the observation. These models have bias to low rank. Take a layer in a neural network, like in a convolutional network, the layers are 4-dimensional tensors. Stick a tensor network there, train, you'll get a low rank solution, and it could be beneficial for various purposes. It might improve generalization, could allow you to compress the model. This is one implication. Another one is a little bit more theoretical. It's a potential explanation for generalization. So one of the reasons why it's difficult to explain generalization in deep learning is that even if you have a result on implicit regularization saying that solutions that are found have minimal rank or minimal norm or something like that, to explain why this thing leads to good performance on test data, there's another argument that you need to make, and that is that it is possible to fit data with low rank or low norm or whatever complexity measure you have. So somehow the data needs to be such that you can fit it with low complexity. And this is not something that can be shown through a mathematical proof because it depends on data and practice. It's a known fact that tensor ranks, and this relates to the question I was asked before, these tensor ranks, when you think of a function as a tensor, look at its ranks, it could actually be shown to correspond to dependencies between different inputs. And it's actually mathematically equivalent to entanglement, to quantum entanglement. Okay, so it's dependencies between different inputs. That means that when you lower the tensor ranks, that means that you minimize dependencies between inputs. So you have an implicit regularization towards local dependencies. And what we show empirically, at least on simple data sets like MNIST and fashion MNIST, you could actually fit them with low tensor ranks. You can fit them with functions that have only very local dependencies. So in this case, you kind of get this complete explanation. The neural networks corresponding to the tensor networks, they lower a complexity measure, these tensor ranks, that actually captures natural data in the sense that you can fit the natural data with low tensor ranks. And so you kind of get this, yeah.
Can I ask a question? When you say MNIST can be fit with low tensor ranks, do you mean a standard way of, MNIST classification, or is this some different task
I
that
do.
you're thinking?
Yeah,
Okay.
I do. What I do here is the following. I have an MNIST data set, and I fit it with I fit a predictor with a tensor. So let me describe it. Let's, for simplicity, suppose it was binary. The data set was, okay. Now, like the class was +1 or -1. Okay? Now, MNIST, that is a 28 by 28 images, right? Either black or white. So I have 784 different inputs, and each input can take on 2 values, maybe more, but let's think of a simple case. So I can think of a function of a classifier as a lookup table with 784 axes. And I will store in each individual entry in that lookup table the label of the corresponding input, right? So if my image had 3 pixels, I could store the labels in a lookup table with 3 different axes, right? A particular image, let's forget about the 3, 784 pixels. Now you give me an image, that means you gave me 784 numbers. Say these numbers were 1 or 2, 1 for white, 2 for black. I will go to my tensor and take that sequence tuple of 784 numbers. That will point me to an entry in the lookup table. In that entry, I store the correct label. That's how I think of a function as a tensor. Now I can search for a function that fits the training data, and I can constrain that function to have very, very low rank.
Yep.
And I can see that even though it has super low rank, that means a really small number of parameters, I can actually fit the data. If the function was rank 1, that means I only need 784 vectors. And if the images are black and white, it's 784 vectors, each one of them of dimension 2. So it's just like 1,500 numbers. And I can fit 60,000 points. So it's kind of much more training examples than parameters, but you can actually fit it. So there is some structure in this data set. And that structure allows you to fit the data set with rank functions. So that's basically what goes on here. Okay, let's move on to the last implication.
There's also a question in the chat, I think.
Okay.
Is a rank 1 tensor related to a naive Bayes?
Just a second, I can't see the chat. Is a rank 1 tensor related to naive Bayes? I don't see any relation that I can point to right now. We can take it offline if there is something that you see. Be interesting to think about. Not something like
because it sounded like you were multiplying values for each input dimension, but maybe I understood something.
Yeah, I guess in that sense, because the independence between features, you mean?
Yes, exactly.
So you can look at these models probabilistically, and in case a rank 1 model will actually mean that the features are, rank 1. So rank 1 means that the features are, from a probabilistic viewpoint, rank 1 means the features are independent. Rank 2 means they are conditionally independent, and you condition on a variable, random variable that can take values. Rank 3 means that they are conditionally independent, and you condition on a random variable taking 3 values and so forth. So in that case, maybe it is related.
Yeah, thank you.
In that sense, yeah. Okay. Yeah. So it's something pretty well known that convolutional nets are not really. They don't really work well when your data has highly non-local dependencies, right? Like if, for example, I don't know, over images where you want to identify symmetry between areas that are really far apart, it doesn't really work well, conv nets. The conventional wisdom is that this is due to their architecture, it's due to their expressive power. Their local properties to the architecture, these local convolutional windows or pooling windows, hence they can only represent local functions. What our analysis shows is that there's some kind of an implicit regularization that also pushes to local dependencies. So the implicit regularization also plays a role. And there's a big difference between these two causes, because if the only reason why they're not successful at learning non-local dependencies is because of their expressiveness, then to remedy this, to improve the situation, you have to change the architecture. On the other hand, if the reason is implicit regularization, or if a reason is implicit regularization, then you might hope to be able to incorporate some kind of an explicit regularization that will counter this bias, that will encourage conv nets to learn non-local dependencies. And we try this out. We run an experiment with CNNs without any regularization, and we compare them to CNNs where we design a specific explicit regularizer that promotes high tensor rank. And then we compare these two models on different tasks. Some of them do not require non-local dependencies, and others do. And what you can see, this is a representative case. I'm not giving the details behind the data set, but it's kind of a task where you can control the distance, the characteristic distance of dependencies that you need to learn. And you can see that when the dependencies are local, both models do well. But when you start making the dependency non-local, the standard CNN deteriorates drastically. But when you add this special regularization, then the performance is much, much better, almost as good as it is in the local dependencies case. So through this explicit regularization, you can improve conv nets on non-local tasks. And this explicit regularizer is directly based on the theory. I'm not getting into its details, but it's basically directly trying to impose high rank, high tensor rank. All right, so let's conclude, and then maybe we'll have a few minute questions. So just to recap, understanding deep learning requires addressing 3 fundamental questions: expressiveness, optimization, and generalization. Today, we focused on generalization, which is believed to stem from an implicit regularization. But this is something that's, this statement is intuitive. Complete formalization of this is something that's still lacking. We used quantum tensor networks as a case study. And we looked at a chain model that corresponds to a linear neural network. There's a conjecture there that the implicit regularization minimizes a norm. And we showed that there's an incremental low rank phenomenon there. That's what the implicit regularization does, and it does not minimize a norm. We then looked at star and tree models, which correspond to shallow and deep nonlinear CNNs. And we showed that there, the implicit regularization lowers tensor ranks. In terms of implications to deep learning, then we discussed parameterizing layers of a neural network as a quantum tensor network that leads to compression. This is something that's actually being done that don't really care about theory. It's just a useful method. We talked about tensor rank being lowered. That might explain generalization on natural data, at least in fashion it largely does. And we talked about countering locality of convolutional nets using explicit regularization. That is based on the theory. This is a regularization that promotes high tensor rank. And just a word to kind of before closing is that I believe that quantum tensor networks can really kind of key to unraveling various mysteries behind deep learning, maybe in general concepts from physics, right? Because one of the big differences in classical machine learning and deep learning is that in classical machine learning, most of the theories are worst case, and they somehow comply with what happens in practice. In deep learning, the worst case theories are still valid, but they are way too pessimistic. And if you try to apply them on practical scenarios, it will tell you that nothing will work. But in practice, things do work. So there is something about natural distributions, natural data, something about the natural world that makes it not worst case. And I believe that reasoning about what natural means and coming up with good models and definitions, this is something that physics is much better at than the classical learning approach. And I believe that there's a lot that can be done here. And one of the things that is being worked on in my lab and will be out soon is the use of these models to try and characterize which types of data are suitable for deep learning. Okay. Use quantum tensor networks and quantum entanglement to actually have hopefully a characterization that's both necessary and sufficient for neural networks to be able to work with that data. Yeah, so that's something that will hopefully be out very soon, and be happy to come back at some point and talk about that. So at this point, I'll conclude. So thank you.
Yeah, thank you very much for this very interesting talk. We do have questions that appear in the chat. Yeah, let's go one by one. Gary, do you want to ask your question directly?
No, not necessarily. It's simple questions. Are there examples of neural network that are not mappable to
Yeah, that's a great question. So first of all, there definitely are. All the neural networks that I talked about today, the biggest difference is in the nonlinearity. And these neural networks that I analyzed have polynomial nonlinearity. The experiments were done with standard common neural networks, but the theories for polynomial neural networks. I did have a work that dealt with generalizing the analysis and analyzing models with ReLU activation, but that required generalizing the notion of a tensor network to something kind of tropical algebra style with maximum and things like that. So that is a direction to analyze other types of neural networks.
Thank you.
Yeah, either read the next question, or
yeah, just go ahead and read it.
I can read it, or Sven. But...
Yeah, do you have some intuition for why implicit regularization lowers the tensor rank, i.e., why largest singular values grow fastest?
Yeah. So my intuition. So I tried to convey the intuition, but think about if you're learning a scalar, and compare that to a case where you're still learning a scalar, but it's a bunch of scalars multiplied by one another. Okay? when you start multiplying numbers, then if they are small, there's kind of this vanishing gradient phenomenon, right? You multiply many small numbers, everything becomes really tiny. On the other hand, if these numbers are bigger than 1, all of a sudden it explodes. So there's this kind of effect where when you multiply many numbers and they're all small, their gradient is very small, but then if they become larger, it starts being larger. That's a scalar case. And then in the high dimensional cases, you basically have multiple instances of that. So that's my intuition. I don't know if it suffices when you ask for an intuition.
Oh, that's good enough for me. Thank you very much.
Sure. Maybe it's possible to have other types of intuitions, but the results are what they are. That's kind of the way I think about them.
Yeah, the next question in the chat is there a way to study generalization further by assuming a particular distribution for natural data? For instance, if your natural data consists of positions of molecules and atoms, a Boltzmann distribution dictates their distribution. Assuming such distribution, can you prove something about this low-rank hypothesis on generalization of such data?
So this is a great question. It's basically exactly what I'm kind of trying to do now, what I mentioned at the end, characterize the distributions in a way that will allow proving things. You can basically say that it relates to the dependencies, whether they are local or global, the profile of dependencies. You can show that in certain cases, if the dependencies behave in a certain way, then it is possible for a model to have a low population loss. It's maybe a little bit akin to area law, right? We know that tensor networks of a certain kind can represent certain states. Like if the state obeys area law, then the tensor network can represent it. Otherwise it can't. It's kind of this small corner of a Hilbert space. So that's basically the analogy. It might sound a little cryptic. Hopefully in a few weeks that paper is going to be out and then it'll be a little bit clearer. But that's the way I think about this right now.
Yeah, I think that's intuitive enough for me. I look forward to what you have on the table as far as this particular question. Thank you for the answer.
Thanks a lot. Thanks.
Oh, and the next one is there any extension you can do from polynomials based on Taylor series arguments? And is this comparison between quantum tensor networks and neural networks valid for arbitrary loss functions?
Okay, so starting with the first. So the extension that I know of is to just change the basic operators in a tensor network. I did not pursue the angle of a Taylor series. There might be interesting things to say there. We haven't done this. It'd be interesting to talk about it offline. Second question, is this comparison valid for arbitrary loss functions? So actually the dynamical results are, they apply to general loss functions. The dynamical results, the result that I showed, for example, that if there's a rank 1 tensor, it's going to be, that actually assumes a certain loss, but the main dynamical results are for arbitrary differentiable losses.
Okay, then so does your conclusion that small initialized matrix factorization minimizes rank disprove the conjecture that it minimizes nuclear norm?
So, okay, so should I answer that? Or?
Yeah, or I can also read the second one. Is there any connection between the minimization of rank, as you described, and the minimization of RKHS norm seen in infinite width neural networks?
Yeah, that's a good question. So first of all, for the first one, it does disprove. There was actually a real kind of theorem that shows that there exist cases where no norm is being minimized. With regards to the kind of NTK style, so these models are not large width models. There is no that's the advantage of this theory. The disadvantage is that the models are polynomial. The advantage is that their size is whatever you want it to be. There's nothing asymptotic going on here. So it's a different type of theory. It does not contradict the fact that in the NTK regime, some norms are being minimized, because I'm not saying that no norm is being minimized in any setting. I'm just saying that in very simple settings where people believed that a norm is minimized, it is not. There are settings where it is. People have proved various results of that kind, and these results are correct, right? I kind of cited them here. So there isn't really a contradiction. I hope that makes sense.
Yeah, thanks.
Okay, there were a lot of nice questions as well. It's a final chance. I cannot
You can always
see.
email me afterwards. Happy to talk. It's
Yes. So as I can see, no more urgent questions. Yeah, let's thank Nadav again for a very interesting talk.
Thank you very much. Thanks a lot. And
Thank you.
happy to